Hello, good evening everyone. Welcome to the third video on how do I generate a heat map based on my CSV file of expression stuff tutorial. Okay, so remember, the end goal of this video is to finally generate our heat map with 6 different subcluster over here with our 5 sample doing actually a row hierarchical clustering and column hierarchical clustering. So row means that you are clustering based on each gene, and the columns mean we are clustering based on the sample. So which sample are closer to another in the column, and which gene is closer to another one based on the expression pattern that I have. So that will be the clustering that we need to do. So just in case you need to understand what is hierarchical clustering, what is the meaning of it, and why do we use a certain parameter that we do, you can actually look at this video. It's actually by StatQuest. So he has a very nice singing voice in the morning, in the beginning. So I find it very useful in understanding of the whole principle around machine learning and statistics. So he has a very nice video on a lot of them. So please check him out, I think. So I do not know him. So personally, I do not understand. I don't know him. I just find his video very interesting. So the first thing we have to do, of course, is to delete everything that we have, because we're going to export. I'm going to show you after this how to export a file to your desktop. Okay, so let's go back to our Rstudio, shall we? So the first column over here, very straightforward, is the HR, means row, so hierarchical clustering. Sorry, I can't pronounce that word. I have a very weird Asian tongue. Okay, so hierarchical clustering. So the first row will just tell you that we are using a Pearson complete clustering method for the algorithm. The exact reason why you use Pearson and complete, it will depends mostly on your data set, and since we're using a random data, so you need to find this out yourself. And how do you find this out is to actually find a previous publication of similar background, of similar ideology, and you just use their method, so you don't have to explain. The other method, of course, if you are really mathematics savvy and you do want to understand, and I will put a few references underneath so that you can have a reference on which method you are supposed to use. But I'm not going to explain here, otherwise you'll make the video about 3 hours long. Okay, so to run this thing is very simple. You just press it. However, just remember you are computing the distance between every single gene, so this will actually get you a very big file. So in this case, it's a data frame of 7. It doesn't show you the file, but if you have, so the calculation get exponentially bigger once you have more data points. So just remember that for 5,000 sample, you need about 4 GB of RAM. So if you have more sample, you need significantly more amount of RAM. Just remember that you have enough RAM before you run this. Otherwise, you need to reduce your sample. So column clustering is a lot more simple because we only have 5 samples. So this is very fast. Immediately it's done. So in this case, this is a card tree. So this is the one that I talked about just now on how to obtain subcluster. So I'm going to come back to that later. I'm just going to run it straight away now. So then we go and run straight away to how to actually plot our heat map. Yes, finally, isn't it? After hearing me talking nonsense for the last half an hour or so. I think it's more than half an hour already. So in this case, the first one is actually the color. So what kind of color do you want in your plot? So it's as a very standard, standard bioinformatics representation. We're gonna use red, black, and green, where red means under expression and green means overexpress. So up regulation and down regulation, very straightforward. Of course, you can actually change this to a million different type of color. So red, you can just put blue, green, you can just put yellow and whatever. So that depends on your need and situation. I'm going to demonstrate that later. So the next one, we're actually going to generate our heat map using a function called Heatmap2. There's like tons of different functions you can use, but I found this one easier to understand. So this is what I'm using now. Okay, so Heatmap2, you have to put in your data, which is Y, which is the one that we have produced in our first video over here. And we followed by a bunch of different examples. Where is my heat map? Okay, so row side color will actually be this one. So row side color will be the card tree that we have generated just now, and we actually generated this parameter over here. Don't need to know if you don't want to understand. So row V will be actually determines the clustering that we do. So in this case, we just put endanogram HR because this is the row clustering. We put in our row clustering details that we have computed just now. column clustering, same thing. So color would be, so COL doesn't mean column. In this color means my color. So my color is the one that I have generated up here. So 75 actually means there's 75 different color in this plot. And the lower expression will be the red, higher expression will be the green, neutral will be the black over here. Okay, so density, we don't want to have any density info, we do not want to have any trace, and we want both of the dendrogram. Dendrogram, if you don't know, is the root like thingy that is beside, and we don't want any key, and the row is scale. We have scaled our data previously, and we do not want any row label because the transcript, there's too many transcripts, so you have row label, you're not going to see them anyway. So let's just continue to run this and stop talking nonsense and start generating some heat map. Okay, so once you've done this will take also a while computationally, not RAM, hopefully. Done, then it will show you in 1, 2, 3. Yes, okay. So you have see here 1, 2, 3, 4, 5, 6. We have perfectly nicely 6 sub-cluster. So of course, there's a lot of try and error before I start filming the video. Okay, so the dendrogram, we have dendrogram for the row and we have dendrogram for the column over here. Nicely as our code as demonstrated just now, and we have green as up regulation, red as our down regulation, and we have a bunch of red over here. So this cluster will have sample C having a lot of down regulation, this cluster will have sample E having a lot of down regulation, and so on and so forth. So that will depend on the context of your research and how do you want to explain it. Okay, so in this case, what do you need to change? There are 2 things you can change over here. Of course, I'm not going to tell you about how to change the method of clustering and the method of all this thing. So I'm just going to tell you that there's a value here called 1.008 as you can see. So this will adjust the amount of sub-cluster that you have. So of course, you can actually see this is the height divided by 1.008. So if you want to have more cluster, you can actually just maybe put 1.5. I don't know how many cluster you have, but you can run the heat map again and you can see how many would you have. Remember, we have 6 just now. Now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, about 20 different cluster over here. Okay, so the higher the amount, the more cluster you have. So we're gonna go back to 1.008. So we have our 6 cluster to represent the 6 group of gene that we have. The second thing you can change over here is the color. So if you do not want a red, black, green, you can, let's say down regulation, I want to have blue box. So because the heat map is not generating, I'm gonna have blue. And over expression, I'm gonna say I'll put yellow because my is yellow and my thing is yellow. Okay, so this one I'm gonna put white. So it's more colorful, everything seems more lovely. So we can run everything again. So we should, because it's 1.008 for the cut tree, we should have 6 cluster, and for the heat map, the color will change accordingly to the thing. Yes, so the yellow will be the overexpression, white will be no expression, and blue will be the unexpression, so on and so forth. Of course, you can change, there's a lot of different color palettes, I think, on R that you can choose from. You can just put something like purple, you can put something like, what else do we have? Green. We already have green just now, but it doesn't matter. So whatever you change, that would be completely up to you. There's a lot of heat, there's a lot of pre-programmed template as well, but I think that's not the important thing we need to do right now. Okay, so the important thing we need to do now is to actually how to generate this graph, because you can, yes, as I said earlier, you can just save as image over here and you will just save in your desktop. Yes, but that's boring and that is not really a good way to generate graph, because in that case, let's try one, isn't it? So let's just run this. Let us save this image as on our desktop. Luckily. Okay, so let's just plot this image and save it on our desktop. And you will realize that we have run into some problem, because when I open this file, here, details. So you realize that the pixel count dimension is very small. That's fine, that's not an issue. But when you have a resolution of 96 dpi, you run into a problem where you try to submit to any journal paper, any publisher that needs to print this figure out. They can't, because 96 is usually only for computer screen or phone screen. and when you print it out on the paper, it looks really blur. Okay, so a good rule of thumb is to about 300 to 350 dpi. So that will be a good figure for publication purposes. So in this case, what we can do here is to try to adjust the information and the settings and details for the export, and as well as directly export it to the desktop if possible. Okay, so before we try to export the plot, we also need to export the details of each of the cluster of the gene. So in this case, we actually use rbind over here. I think I did not actually talk you through all this, but in this case, I'm trying to put the cluster information into my genetic information, and I'm trying to save the file as CSV as my desktop again. So you can see this output file that I just generated. So in this case, if I open, you realize that it will look exactly as the thing that we done just now. So we have a gene name, we have all the expression, the normalized log transform expression, and this will be the cluster that they were in. So you can actually, if you actually don't know how to do the sophisticated R way, you can actually just do this. I want to talk largest to smallest. So you get all the gene for cluster 6 to do whatever analysis or enrichment you want. So if you only want group, let's say you only want cluster 4, let's say. So yeah, so you get all the cluster 4. So you get all this about 2,000 different genes. I'm not sure how filtering in Excel works. I'm not using Excel. Yeah, about 1,000 plus gene cluster 4. So you can actually do whatever enrichment you want based on that. So in this case, you are able to isolate a bunch of transcript out that you can able to do whatever you want with it after this. Okay, so once we are done with the file, let's try to generate some figures. Okay, the first figure, of course, we're going to generate is the heat map. And in this case, I'm using a PNG format because TIFF format is very big. PDF format doesn't actually allow me the flexibility to manipulate, and it's quite hard to integrate. Let's say I want a PDF into a Word file like I usually prepare my journal article in. It's very difficult, so I usually use a PNG. PNG have a relatively small file size and actually quite a very good DPI. So in this case, the first row over here, PNG, is telling the R that you are going to generate a PNG image. Okay, so and this long thing over here is absolutely not necessary, but because I don't like to overwrite my file, what this does is to save your file as the current time and date. Okay, based on this year, month, date, hours, minute, second. So in this case, you will save the file as a PNG using the current time and date. Okay, so every time you export, you will not overwrite the old file. Okay, so the one in the back is very straightforward. Width is 12 and height is 10, and units in inches. So the actual size of your PNG will be good enough for a 10 inches times 12 inches paper, which is around the size of an A4 paper. And this is the important one, the 300. So this is the DPI that we talked about just now, the dot per inch. So if you want publication paper, you need a 300 DPI. So we set the working directory to our desktop. So we want to save our file to the desktop, and we rerun the whole heat map again. Okay, so you realize that there's no way to input any file into that, because this command will actually catch just collect the next program that generate a plot and then save it as a PNG. And of course, you have to run device off, otherwise you keep on informing and only import one. So in this case, the PNG, this command always follows by device off. Whoops, what did I do? Okay, so it will always follow by this device off. Okay, so in this case, what we have to do is to run everything at once as if it is one command. So let's just run this again. So you will set the heat map again, and so forth. Then you wait a while. Then yeah. So once you get done, you still get a Rstudio GD of 2, and then you go to your desktop. Yep, it's here. Hey, where's my file? Okay, it doesn't work. Okay, that's a little bit awkward. Let me check what happened. So that directory file offset, let me check file over here. So yeah, it has not saved to desktop. Apparently I have something wrong with my directory, but you can see this is the current time and date, this one. So which is 10 o'clock. So we have actually successfully generated our heat map over here. So of course, if it's not in your working directory, which could be some authorization problem from Windows and such. So this will actually generate a file into your current work directory folder, and so on and so forth. It depends on where you set it and where you open it. But if you don't really know where to find, you can just find the file over here, and you can actually find this. So this will have again. So let's just make sure that we did not screw it up and I do not actually teach you the wrong stuff. Let's run it again, and you see a new file generated right here. Okay, 3, 2, 1. Yes. Oops, I'm sorry. Okay. Okay, now it goes to now it goes to my desktop. I have no idea how this works and why it does that. Okay, so now it goes to my desktop. As you can see, we have exactly the same thing. Let's just regenerate this again in mind, because there are some errors that they are not familiar with. So let's just generate this again, just to make sure that I'm doing it correctly. I might actually just cut this and then just make sure that yep, it got generated perfectly. So the code worked perfectly, there's no problem with that. So once we have done the heat map, you can actually done everything the same way. So you just run. So if you do not want to understand the code is exactly the same. So you just press run and everything will work. And as you can see, the feed class over here, the elbow method would take a little bit longer, and you wait for it to generate before we can actually have everything. So it might take a while, so I'm just gonna say thank you for watching. I hope actually everyone has learned something out of it, because I sure has a very hard time adapting to this R environment coming from SPSS and such. Okay, so now we have done everything. So let's just go back to our desktop and check what we have as our output. Okay, the first one, this is not relevant. So the first one, we have our heat map. The second, we have our Hierarchical method. The third one, we have our elbow method over here, and the last one, we have our K-mean clustering, which might or might not be useful based on the situation that you're in. So I think that's hopefully will help everyone to do some heat map and clustering and write some papers. And thank you for watching Breakfast for Living.